So let me start by first saying this talk is an expanded version of a panel discussion that we had at last year's AES meeting in San Francisco. There was other participants from Qualcomm and audience, and the topic was on the general area of using multi-microphone arrays in mobile devices. So I'd slightly fudged the title of the talk a little bit. It's entitled Differential Microphone Array Usage in Android Mobile Device Multimedia Application, because I decided to spend a little bit more time reviewing microphone arrays and microphone array fundamentals. So this is my name and affiliation with Motorola Mobility, part of the system design group, the core audio and acoustics team. We do all things audio in mobile devices. And let's start with this. I will start with an introductory slide. I'll have a couple of slides just to introduce the topic and show a short timeline of when it happened that all of a sudden we decided we needed more than one microphone in these things. Then I will spend some time talking about the fundamentals of beamforming, and we'll look at delay and sum beamforming, which is everyone is familiar with, and we'll then talk about the fundamentals of differential arrays. With the differential arrays, I'll show my favorite derivation of what a differential array does, and it will demonstrate the directional response and the frequency response of the array. Then we'll dive into a simple, what I call simple beamforming pattern arithmetic, and what that will do, it will tell us how we go about forming various virtual signals that have desirable directional properties using some fundamental components. That's useful to look at before we go into discussing the application of interest here, which is none other than enhancing the audio capabilities of the video camera that was coming stock on the Android platform. Then we'll show a slide on the actual implementation of the microphone array, and we'll discuss what it takes to make it working, after which we'll show some examples of example realizations of real signals, example realizations of the audio modes that we have in the camera. Then we'll discuss a little bit the control aspects, particularly the user interface, and what one needs to be aware of when designing something like that. Then we'll talk, they will have a couple of slides on other fringe benefits of the using of the microphone arrays. And then one of the probably most important slides, the implementation challenges. That's probably a presentation on its own. There's one slide here, but I can probably spend weeks talking about that. Then it's movie time. I will show a short demo illustrating hopefully the benefits of the application that we're talking about, and then we'll summarize it and conclude it. So before I go, I just wanted to put a disclaimer that hopefully those of you that are really very well versed in the topic of microphone arrays and beamforming, I apologize, this might be a little bit boring for you. Those of you that are not, hopefully you will get something out of it. And with that, let's go to the next slide. Basically, up to about 2004, 2006 time frame, everything that was sold on the market had one microphone. There was just no infrastructure, there was just no perceived need, there was just no way to put more of these things in the devices, simply because there was no perceived need for it. Eventually, starting about 2006 onward, we had developed dual microphone noise suppression algorithms. They were mature enough, robust enough for product implementation, and they found their way into handsets. So much so that from about the 2008 or 9, I don't know the exact date, some of the carriers mandated the use of dual microphone noise suppression algorithms, and I think AT&T requires that all devices that they put on the network have multiple microphones. In 2010-ish time frame, we started seeing actual devices on the market that featured more than two mics, and one example of that was our own Millennium device, which was multimedia centric, and it's the device that this feature that we will be talking about was developed for. So over the last couple of decades, these devices that started as a basically very fundamental communication system that could that you could make a phone call pretty much or send very little data or a text message, they started developing and morphed into these very complicated and complex systems that allow content creation. They are always on, plugged in the network and in the cloud. They are useful for many things. And all of a sudden, the voice call and the voice functionality of it seemed to be taking somewhat of a back stage. It wasn't really that important that you can make a phone call because no one is using the device. Well, the device is used for so much more other than phone calls. And one application that we were particularly interested was video capture. Video capture is really a fruitful area for these things because it allows the user to get a short message that enhances a multimedia text that they will send. They can upload it to their favorite social network. They could upload it to YouTube. They can share with the world. But they could also use that and hopefully replace their camcorder. So they would use the device that is always with them to capture family events and then share that with family and consume that multimedia over a home theater system, for example. All of that meant that we started seeing the need for proper audio. Not only were we getting good video, which now became cheap, sensors became available, but all of a sudden we have a need for a really good quality audio to go with that high quality video. And so that necessitated good signal to noise ratio, decent frequency responses, wider bandwidth in the recorded audio, and multi-channel audio was next in line because multi-channel audio starting from stereo, maybe higher formats, were meant to greatly enhance the sense of immersiveness of the video that you're recording. Here is one example that illustrates a device that is somewhat audio-centric, and I'll quote that's a quote from TechCrunch. It's a versatile and useful pocket cam for people that value the audio portion of their video. Very nice. And as you can see, the device, by the way, doesn't shine so much for its video properties, but the audio was decent on the market for the price and for the application. As you can see, this device features a pair of microphones oriented at an angle. So all of a sudden, we had enablers in the industry that allow us to record multiple channel audio. And what are those enablers? Well, codec technology was mature. And by mature, I mean codec technology was cheap, affordable. You could license the codec for a large number of handsets or devices at reasonable price. Stereo recording techniques have been known and developed. Everyone is familiar with them, and we know One way to capture stereo is using omnidirectional mics at some distance away. Another way is how the Zoom device approaches it with a pair of coincident mics. Multi-channel recording techniques, that's a very fruitful topic, basically necessitates even more microphones. Now, in an audio-centric device like this, this is fine. This is actually the directional response of the two mics that you see here. In a cell phone, none of this is actually possible. The cell phone has a different form factor. It will have to rely on some processing or some combination of the signals in order to achieve directivity and meaningful content separation in multiple channels. And that's more or less the topic of the rest of the talk. Let's start with a brief review. When we say beamforming, everyone tends to think about the delay and sum microphone array. And what the delay and sum microphone array basically works by summing appropriately delayed signals, sometimes delayed and attenuated signals on multiple branches from a set of sensors. This shows the directional response of the array, neglecting the time term. And the purpose of the delay on each of the branches is to make sure that the summation at that node is coherent. In other words, all the signals that go in that node sum coherently from the direction of interest. So the delay and sum beamformer can steer its direction of maximum sensitivity simply by adjusting these delays in each of the branches. And let's see how that is done. If we have a source of interest, this subject, and that source of interest is at some angle alpha, a plane wave arriving from that subject will first hit the first sensor and will hit the nth microphone sensor last. In order to synchronize all of these signals before they go into the summing junction, we have to apply maximum delay on the line of microphone 1 and do not delay the last line. Now, suppose that at the same time as this subject as we've steered the array in that direction, we have a source of noise that is at some other direction. What will happen for that source? We notice that the sound from that source will propagate to microphone N, will hit microphone N first, and will hit microphone 1 last. Now, we already delayed that microphone. We're not delaying microphone N, we're delaying every other microphone with respect to N. So the result of that is that we have a signal that is out of coherence when it hits the summing junction, and this summation does not result in enhancing the signal's amplitude. Okay. Now, this looks easy to appreciate. It has one very big problem. That big problem is that the frequency, the directivity of the array is frequency dependent. In practical terms, when this is realized, the cousin of the delay and sum beamformer we call filter and sum. And filter and sum because the delay in each of the branches is realized using a digital filter most often. The reason for that, and that's important, we'll get to that later in the presentation, but what that achieves is that for a real system which is not transparent, different portions of the signal have to be advanced or delayed appropriately. So each frequency has to be delayed appropriately. Usually, these filters come, their coefficients come out of a filter bank. They're selected for a specific lookup direction of the array, or they could be calculated on the fly. For example, if one were to use a fractional delay filter, and if one were to steer the lookup direction of the array, these fractional delay filters can be easily calculated on the fly if that's how the array was realized. Let's look at the the other way of doing things, and that's the differential microphone array. The differential microphone array has a number of benefits. And first and foremost, it can achieve very high directivity compared to the delay and sum beamformer with the same number of sensors. And that's important because in small form factor devices, we cannot actually use many sensors. Having said that, the delay and sum beamformer is used as a constituent part in more complicated structures such as the generalized side lobe cancer, Griffiths-Jim beamformer, and so on. The differential array, though, is very useful for application like ours because it is very cheap computationally and has some really nice desirable properties. Most of all, it has constant directivity with frequency, and that is important because it allows us to get a broadband signal directional in the way we want. Another important difference compared to the delay and sum beamformer is that the delay and sum beamformer steers the direction of maximum sensitivity in some desired direction, while the differential array operates differently. It steers the null, or that is the direction of minimum sensitivity, in a desired direction. The differential array has its maximum sensitivity always in the direction of the line connecting the two sensors, always. The null, or the minimum sensitivity of the array, could be steered in other directions. And that's why in the art, this is usually referred to as an end-fire array, whereas the delay and sum beamformer operates in a broadside direction also. Another desirable property is that the differential microphone array has been looked at, and various adaptive algorithms have been developed for steering the null in a desired direction, simply because that involves minimizing energy, and this structure lends itself very usefully for that purpose. I don't want to sound like a car salesman here, but one thing that we notice is that the beamformer output is not flat. We'll see that in more detail, but basically what it means is that the differential array requires additional steps of equalization for its output to be useful. That bullet was intentionally promoted just to illustrate the fact that if we had few of these producing signals of having some fundamental property in terms of directivity, linear combination of few of these will allow us to steer nulls and to get signals of various desirable directional properties. So it's a very useful way of thinking about it, and we'll talk about that in the beamforming arithmetic part. And so let's look at that example. How does the differential array work? Well, first of all, there's two microphones. They are located at 2 points in space, so we really are exploiting spatial diversity. And they work to find a directional gradient along that line. And the gradient of the sound field approaching will be the directional gradient will be maximum if the source of origin is along the same direction. Now, the derivation for this is in Elko, but basically if you look at the output has this term of cosine theta, where theta is the angle between the direction of the array and the direction of propagation of the sound field coming from distant source, resulting in a plane field. This illustrates that whenever that angle becomes 90 degrees, the output of the array is minimum. Whenever that angle is in the 0 or 180 degrees direction, this expression has a maximum. So as a result of this system, the way it is written, will have, the way it is plotted here, will have a response that we call a dipole. It will have a null oriented along that line, and it will have peak maximum sensitivity along that line. And we will see how useful this is on the next slide. Now, this features the same, basically the same block with an extra element added to it, and this is a delay block. The function of this delay block is to be able to steer where the null or the direction of minimum sensitivity occurs. Did someone say? Was there a question, or did I? No? Okay. You can interrupt me and ask questions if you wanted. I think we will have a question and answer session at the end of this. So let's see. We'll look at the derivation of the response of the array in a little bit. But basically, the goal of this would be to show the array response in terms of a directivity and frequency term, which would explain why and how we can design arrays with desirable directivity, and what do we do about its on-axis response. And now let's look at this a little bit intuitively. If we have a distance between the two sensors of d, and we take the ratio of d and the velocity of sound, that is the maximum acoustic delay that will be seen. This is the maximum acoustic delay that will be seen for a signal propagating along the line connecting the two microphones. The acoustic delay, or the difference between the two signals, will always be smaller, and it will be smaller by exactly this term, when the direction of propagation of the sound field coming from a distant source is at some angle theta. Okay. So now the next thing that we notice is we define this term which is located at the exact geometric center of the array, and we call that a phase center. We only use that in order to define and calculate what the signal output would be out of microphone 1, which is this, and out of microphone 2. And all that this says is that the signals out of microphone 1 and 2 would be delayed with respect, if we had a sound source located like this, will be delayed with respect to the phase center or advanced with respect to the phase center. Okay, so now we will look at the output of the array at this point, and that output is nothing else other than the difference between x1, x2, half of it, where x2 is actually additionally delayed by this much. How much? As much as this block defines. Next thing that we do, we notice these common terms. We take that term out of the brackets. We take this extra term out of the brackets, and we're doing this in order to render this expression inside in some familiar form. What that form is becomes very clear when you look at this line. We're basically multiplying by j and dividing by j, and this expression here looks very much like an Euler formula expressing Euler formula expression for a sinusoidal function. Okay, so we replace that with the sinusoidal function, and we get this expression here. With some grouping, we get to that final line. Now, why did we do all of this? Well, we did all of this because we want to find what the transfer function of this system is, and we find that transfer function by looking at the output with respect to the signal at the hypothetical phase center. And this is what happens here to derive this term. And now here we do another trick, And that trick everyone is familiar with. And the trick is that when sine x is equivalent to x, when x is very, very small. And that's what happens here to get us to this point. At this point, we notice two interesting things. The first one is this. Well, actually, the first one is this. And what this looks like looks very much like the cosine term that we saw in the previous slide, but it has this extra contribution to it. And what this extra thing does, we'll see on the next slide. And this term is important. This term defines the frequency response of the array, and what it does, it makes the array behave as a high-pass filter with certain slope. In other words, the array starts, this defines why the differential microphone array is lossy at low frequency. Let's go to the next slide. Okay, so here we are talking about, I hit a snooze, I'm not sure what will happen here, but hopefully there's a little clock. So this is what happens in the array in terms of directivity. So what is happening here? Well, let's suppose that we have a delay, this theta over theta A that we saw in the previous slide is equal to 1. In that case, this delay will be the same as the maximum acoustic delay that the signal can experience along the axis between the two microphones. Well, what does that mean? Well, suppose we had a source that was located here. The signal from that source exactly on that line. The signal from that source will propagate to microphone 2, and then after some delay, which would be the maximum delay, will propagate to microphone 1. At the summing junction, the two signals will find themselves in phase, and they will be identical, and they will be cancelled out. And the output of that system for a source located here will be 0. This is what happens here. This is exactly what happens here. At the 180th degree, we have a 0, and that is the cardioidal response of this system. Now suppose that we put that delay to be 0. If that tau, if we do not delay that signal, what we've effectively done is we've rendered the system to be exactly the same as the system that we first looked at. And what that means is that at 90 degrees, the output of our microphone array will be 0. And one thing to notice is that this is axially symmetric. The array itself cannot differentiate whether the signal propagates from the left side or the right side, because the delays in both branches will be identical in both cases. Now, between those two cases of dipole and cardioid, there's various other possibilities, various other limason or limacon patterns that are obtainable just by varying that term, tau, or the amount of delay that we introduce in the system. Okay, now we said that this is all fine, and let's look at what happens with the frequency response of this system. And this is what happens. It's a first-order high-pass system, and from some frequency onward, downward, the system attenuates. Why does it attenuate? Well, it attenuates because this space diversity that we have, this distance that we have, as the frequency is reduced, for lower frequencies we have larger wavelengths, and in larger wavelengths the differences that we are obtaining will be smaller and smaller and smaller and smaller and smaller. So much so that this system will have some low-end low-end limitation where the microphone noise itself becomes a problem, and we can do nothing about that. And what that means is that the system, for it to be useful, we need to equalize it. In other words, make this flat with a filter with inverse properties. Typically, now let's look at what happens over here. There are spots there are parts of the frequency response that the on-axis of this, or the on-axis response of this system has these valleys where the signal is cancelled. This is easy to see that these nulls occur because of the sinusoidal term that we had in the response of the system. But it's also easy to think about this in terms of the response of the system with respect to frequencies for which the wavelength of the signal becomes smaller than the maximum distance that we have, the physical distance between the two sensors. What I'm trying to say is that there comes a point where the system cannot actually resolve where the signal is coming from, and it will start placing multiple nulls, or in other words, it will start cancelling signals that are coming from directions other than the one we intend. All this goes to say that the ideal operating area for the differential array would be somewhere in that range. And the microphone array designer will have to take this into account when they design the system, and will have to do something about it. What can one do about it? Well, there's multiple approaches to it. One can identify for the given system what part of the bandwidth, what part of the spectrum we can beamform in, and concentrate on a subband that this is possible for the given microphone array configuration, and just do the beamforming there. Another way to look at this is what is known in the art as hybrid arrays. And what hybrid arrays are, they take a signal from pairs of microphones that have various distances between them, so they're geometrically designed such that these points of cancellation occur differently at different frequencies. What all that means is that one could take a pair of signals, low pass, filter them, do the array on that bandwidth limited signal, equalize it. Similarly do the same for a closely spaced microphone pair, and when it's all said and done, the overall response of this system would be much better. Its response will be extended, in this case, by an octave with respect to a system that would use only one microphone pair. I wanted to mention this. This isn't so simple in the sense the system engineer that works on this, they will have to make sure that the equalization is done properly, that the group delay on all the branches is done properly, so that when the final mixing occurs, the signal recovers and reconstructs properly. Okay, so I have a few slides on this beamforming pattern arithmetic. And what that is meant to illustrate is that if we have two systems or couple of systems that produce some fundamental components, by combining these components, we can get a signal that has desirable spatial properties. An example of this is two dipoles that are obtained from two orthogonal pairs of microphones. One of the microphones could be shared theoretically. When they are added together, they can produce a dipole oriented at 45 degrees. Or in other words, the effective null will be in a different direction than that of the original two dipoles. The same goes down here. It's just this just illustrates that similarly, just by simple arithmetic, we can produce a dipole that's oriented at a different direction. And in fact, one could argue that by varying the amount of each of these things, each of these two signals, one could steer the dipole in any direction of interest. Why that's important will become clear next here. Here what we'll notice is that, and I just want to mention that the devil here is in the details, how exactly this is weighed and how much magnitude is we get from one signal or another. But here we notice something else. If we had a dipole signal and an omni signal, and we magically out of two different components, and we sum them, we'll be able to produce a cardioid signal with a null steered at some direction. Which direction would that be? Well, the dipole will have two lobes that are out of phase. The omni, when summed with the dipole, the signal, the out of phase signal will cancel out, and it will produce a null in that direction. Similarly, if we had a dipole in a normal direction from a different microphone pair, we could produce a cardioid in that direction. We can produce a cardioid by reversing the polarity of the dipole. We can produce a cardioid with the null facing the opposite way. So we can produce a lot of this just by summing the different component signals. Now, the other interesting thing to notice is that the amount of dipole and omni signal that we get will determine what's the actual directivity of the signal, of the composite signal that we'll get out of that. This is supposed to be a hypercardioid, but it wasn't drawn very nicely, but this is the formula for a hypercardioid. And intuitively, if we go back and look at the formula in the previous slides, we will see that we had a cosine term plus another term that could be either one or something else, and depending on the time delay that we introduced in the system, and as a result of that, we were able to produce various limaçons. Okay, next slide. I don't mean to bore you with all this, but basically what that tries to illustrate is that if we can do a dipole at any orientation, nothing is stopping us from producing a cardioid. That is, if we have pairs, if we have signals from orthogonal microphone pairs, nothing is stopping us from producing a cardioid oriented in that direction. Or alternatively, if we had some linear combination of cardioids, we could produce them, we could steer them in a direction that we would like. And why this is important will be appreciated hopefully on the next slide. And this is a little busy to look at. But when we started talking about the feature, we were thinking, okay, we have this video camera. We can capture signals from multiple mics. We can produce virtual microphones. We already know how to steer their directivity. We already know what to do with them, how to orient them. What do we do with all this? Well, what would be useful for the user? So we thought a subject mode would be useful. What is a subject mode? Well, we'll define it as a mode that maximizes the signal in front of the device and minimizes the signal on the display side of the device. So what I'm showing here is a side view of a Millennium phone. The camera is located in this bulging part here. This is the display side, and this is the rear, the back side of the phone. So typically when we operate it, the operator will be holding the phone, and the subject of the video will be somewhere here. So the subject mode will try to enhance all signals coming from the back of the phone, and will try to attenuate all signals coming from the front or the display side of the phone. Okay. What else could be useful? Well, we thought about this balanced or narrative mode where we could use it as an interview, where we would be able to better balance and better equalize the two signals. Stereo mode, concert mode, well, if we have all these microphone pairs, we could realize various interesting things like cardioids pointing to both sides of the microphone, or something more complex. Basically, these pairs of microphones would mean that we could possibly have multiple different channels separated by the sensitivity of that virtual microphone. We could talk about realizing some other neat features like zooming, microphone zooming. We could think about doing this using varied beam pattern. We could do that by beam steering. And another interesting thing that we were thinking about would be wind detection and suppression. Okay, all of that led to very specific requirements that at minimum one needs to have multiple mics, so you would like them spaced in certain way that you can't really get, because at the end of the day, everything is a compromise. So this device being multimedia centric is after all a phone, and it has to support voice features, it has to support speakerphone, it has to support handset phone calls, and so on. So that imposes other requirements on the on where the microphones are placed. Okay, so how do we realize some of these things? Well, subject mode could be realized by taking the two signals out of the bottom microphone pair and creating an array that steers a null in the direction of the display, and it steers a lookup along the direction, in the direction of the back of the phone, where the subject of the video would happen to be. The interview mode could be realized by some other Limacon pattern using, again, these two microphones. Other modes, stereo mode or a concert mode could be realized by using the far microphone pair to produce sideways oriented virtual microphones, and the bottom microphone pair to realize a forward-oriented virtual mic. All kinds of possibilities. Here we try to illustrate the microphone zoom by beam pattern variation. And if we were to start with this with the bottom microphone pair and form cardioid oriented towards the subject of the video, and we already know that that pattern can vary. As we vary that pattern through from cardioid through hypercardioid, dipole, inverse hypercardioid, inverse cardioid, we will effectively reduce the width of the audio that we're picking up in the direction of where the subject will happen to be. Other neat tricks could be we could combine multiple, or two in this case, stereo signals, matrix them in this way, and produce a signal that as we zoom, in other words, as we synchronously change the field of the viewfinder of the camera, will become increasingly monophonic. And that happens to create a nice effect there. That brings me to the next slide. And this slide is entitled Microphone Array Fundamental Built-in Block. Everything that we said about the differential array, all that derivation that we showed, is technically true but it only helps us in the case when we are dealing with a transparent array. And what a transparent array is effectively two microphones with nothing between them. Well, these things, they don't look like that. So what happens is you have two or multiple microphones, and there's a fairly large structure in between. And what that structure does, and the porting of the microphone and all of that goes in there, results in complicating the life of the system designer. Because what it does, it creates the necessity of designing a proper delay filter that delays every frequency just right prior to the summation junction where the differential occurs. That's the secret part. Although if one looks at it long enough, it wouldn't be that secret. Anyway, so using that fundamental block, we will get some output. That output would be equalized. We already saw that we need to equalize whatever signal we formed out differentially. And that would produce us some pattern. In this case, we're talking about forward cardioid and rear cardioid, but it could be something else. Having all these different signals with various directivities, we looked already how useful they can be. So what we said here is this could be a little bit more complicated. Obviously, it could be used in subbands. It could be followed by an adaptive stage that does other interesting things. But that's a more complicated topic, and we won't go into it. So let's look at an example of this. And it's kind of a busy slide, but here is what happens. We have a microphone array comprised of those two microphones, microphone 2 and 1, and we are trying to sound the array, illuminate it with energy, and see what the array response will look like. And to do that, we use a source of energy, a speaker. We play some band-limited pink noise, and we try to rotate the speaker around the geometrical center of the array. That allows us to, when we do that for some period of time, that allows us to see the individual microphone responses, and it allows us to see the final array response. And when we look at the individual microphone responses, let's look at microphone 2. We see that when we start, our microphone 2 is facing the source, that's right here. And as we rotate the source around the array, somewhere here, the source is now facing microphone 1, and microphone 2 is behind this big baffle that phone is. Consequently, microphone 1 is able to see a lot more signal in that place. Okay. The actual directivity that we get out of the microphone 1 and 2 signals, there's obviously some directivity. The actual directivity is on the order of 4 dB, 4.5. It's obviously band limited. It is frequency dependent. Anyway, so those two signals are then combined, and we are producing a differential array with the following output. Now, this looks a little bit more directional. What does this show? Well, it teaches us that the array will have maximum sensitivity in the direction of the display, in the direction of the subject, and it will have a minimum sensitivity in the direction of the display. And when this is all said and done, it all happens to be on the order of little over 20 dB, 24-ish, I think, in this case, when it's actually measured, when the signal is actually measured. Here is another example of this. This is the array. This is the microphone array response in subject mode for the Razer phone. I have a couple of those phones here. I can show you if you're not familiar with them. And again, the operator in that case is attenuated, but by some 20-something. 24, let's call it, dB. That's what this illustrates. But it's the actual directivity of the composite virtual microphone signal. Another example of this is a phone called Droid. It's the Droid 4. Android 4 was a very nice phone to be designing an array due to its microphone location. The microphone location was very much on the edge of the phone, and that makes things a lot easier. So this is the response of the stereo audio mode realization. Basically, we see that we are steering a null to one direction in the left, which would that be? That would be the right channel, and a null to the right direction in the left channel. This is an example of unrealized. This is an unrealized thing, but it serves to illustrate how, using a proper microphone configuration, one can create a surround sound implementation of fairly good quality. That takes us to the next topic. And anytime you're trying to do something that the user will select, one has to worry about how would the user interface look. Okay, we're trying to design this feature, and we are trying to make the user aware of it, and we're trying to make them understand, appreciate how useful it is, and to have them select various attributes for the audio. So when you talk to the audio engineer, they want all sorts of possibilities, multiple ways of doing things. When you talk to the design people, they say, no, with this thing, less is more. 2, 3 maximum, no more. So depending on the compromise, what ends up happening is we come to an agreement, and we have several of these scenes that the user can select with selecting this icon. And notice that since the feature was so important, this was icon number 1, and that's the only icon that the user will actually notice, the top icon. So those become a lot less important, although that's a very nice icon. That's the light, and it's used just as a torchlight for the phone. But so then when we select the icon, we can select one of multiple scenes. And here is another problem. One is asked to describe what is it that this does. And but this has to be described in 125 characters or less. Well, that's not easy. So that's another problem that an audio engineer has to come up and solve. And it just isn't easy to do. Anyway, we're coming to the next slide, and that slide is titled Other Benefits of Using Multiple Microphones. So when we realize that, okay, we're using inputs from multiple microphones and we're doing all these neat things with them, that carries some baggage with it. And one of the things is multiple microphones, differential arrays, they tend to be susceptible to wind noise. Why? Well, wind noise is not coherent in the multiple sources. So it is not something we can cancel with the array. This lack of coherency means that if it appears, it's only amplified. If it appears in multiple mics, it gets worse. What can one do about it? Well, mechanical countermeasures are really difficult. A bonnet, they don't make bonnets for these phones. And even if they made them, I don't think that anyone will buy one other than us, ourselves. This looks very silly. But one has to notice that over time, algorithms were developed that could take advantage of the signals on multiple microphones and make some decision. What decision? They can either detect that wind noise happens and warn the user and tell him, shoot in this special mode that does something to the signal, for example, as a countermeasure. Or even an automated multi-microphone wind noise suppression could be enabled. That's easier said than done because these things tend to be computationally expensive. And we'll see on the next slide how important this is. Another problem that other people do not deal with, and I mean by other people, people that design proper cameras, is the susceptibility of the device to handling noise, microphone occlusion. And all this results from the factor. I mean, it's a very small factor device. The user is not aware where the microphones are, and even if they were, they don't know what that means. The user places their hands everywhere, and all that creates all that rubbing on the body of the phone can create, believe it or not, fairly sizable amount of noise in the microphone line, which will show up when it shows up on the home theater system during playback is not very nice. It ruins the video. Fortunately, the other problem is occlusion. So it so happens that placing the microphones where you want them makes them very easy to occlude, because the user will do this. When they do that, well, guess what? They just put their hands on the microphones, at least one of them. Now, one very nice feature about the microphone array is that there's an implicit built-in diversity in it, and there's an implicit built-in robustness that if we occluded only one of the mics, that will not destroy the audio, in the sense you will still have audio in the video recording. It just is going to be in a rather poorer quality. It will be slightly colored, but it will be there. That being said, algorithms exist, and it's a fruitful development topic to detect that occlusion occurred and to warn the user. And one would ask, why not just do something about it? And the answer to that is, if you have a smartphone, they should at least appear to be smart. And that brings me to the next slide, and that is implementation challenges. Well, as with everything else, challenges are plenty. When we started, when we started looking at this, microphone placement is, as we said, is very important. Unfortunately, microphone placement is one of these things that has to satisfy requirements that are so diverse and so difficult to satisfy all at the same time. What are they? Well, use case. Whether you use the device in handset mode or in speakerphone mode, that places some requirements, implicit requirements of where these microphones need to be. Radio. Thou shalt not interfere with any radio functionality. The radio is the most important part of the phone. Well, that means if you have to place a mic where the antenna is, tough luck. You cannot do it. Aesthetics. Who would think of that? But it turns out that if you talk to an audio engineer, they want to have a phone that looks like Swiss cheese, because they can do a lot with that. But if you talk to a user experience designer, they want to see a phone that has no holes whatsoever, and preferably no mics, because microphones need holes. So it really becomes a balancing act, and in order for you to produce something that is reasonable, many diverse requirements have to come to, all the stars and planets have to align. That said, what else? Microphones need to be matched in response. It's well known, we didn't discuss it, but it's a well-known fact that the differential array is particularly susceptible to microphone differences. So that imposes some requirements to the microphone manufacturer, and when you tell them, well, we want these microphones to be plus minus dB, they, oh, why? No one wants that. That becomes a problem. Now, all this leads us to say that it really needs to be an audio-centric device. And as we said at the beginning of the talk, audio is no longer the center of this. Other things are. So it's very difficult to promote audio to the point where someone will sit and listen to you and say, okay, let's do that. Okay, that makes sense. Now, other problems that we face, that's the algorithm and the software component aspects. When we combine outputs of multiple sensors, whether those are microphones or antennas or whatever it is, we only end up having more noise. The more inputs we have, the more noise we have to deal with. We have to be very careful with what we do with that noise, how we write the processing code so as to not amplify that noise. And this quickly becomes a problem when you talk about fixed point arithmetic, filtering, and so on. All of that necessitates careful attention to be placed all the way when the algorithm is being developed. Algorithm can be developed that at some point, when the implementation comes, is very challenging and even non-workable, non-starter. The other aspect of this is that we are dealing with a portable device. That portable device uses battery to be operated. And current drain is a big issue. Everybody wants their phone to last for a long time, their phone battery to last for a long time. And there is this group of people, we've never met them, but we know they are there, who look at the profile, they profile what happens, how much all the different components, how much current they draw. And if you draw too much current, you immediately are flagged as do something about it. To not have to deal with this, one has to incorporate this into the algorithm design from the very start. And that's not easy. Once the component is written and works great, the next point is integrating it. Okay, we have integration engineers, but they have to worry about all sorts of things. Where do we put that? Do we put the code in the hardware abstraction layer? Do we put it in the application layer? What parts of it? How do we separate it? How do these parts talk to each other? And there's all kinds of other aspects that the component designer didn't think about. For example, if we're shooting a video and a phone call comes in, what do? Do we send a ringtone? You can imagine what will happen if that ringtone happens to come during the time of the video. How much signal will that put in the two mics? That's not acceptable. So that means, well, we have to be sending some notifications. Visual notifications on the screen mean that someone has to go and do that. That is different from the vanilla Android drop that you get from Google. Various other aspects like this. For example, can we, or many governments in the world require that you play a shutter tone when you are shooting a video. This means that you have to power the speaker for a certain amount of time. When do we start the video? Because if the speaker is still powered, we can hear it. Things of that nature. The system engineer that does the final design, once the component and everything is integrated and we are in production, they have to worry about performance optimization. And in order to design the array properly, they have to do various types of measurements, and they would need to do that on the final hardware. Final hardware isn't available. Usually it's late, it comes late in the program, and the person that has to deal with this, their work starts getting compressed very, very much to the point of where they have a day to complete a fair amount of work to verify and design, and it becomes difficult. And now, that takes us to the movie time. And the movie time is basically, we'll show a short video that will demonstrate the benefit to the user for a video shot in subject mode. This is one of our colleagues, Kevin Bastier. Many of you know, maybe you know him. He's one of the people that worked on the team. If you were to come to us, either Kevin or Rivo or Giles will be some of the people that will demo various features about this. And what Kevin did, he wanted to show what happens when he is in front of the camera, where his voice is intended to be amplified, versus when he is in the back on the display side, where his voice is intended to be attenuated. Let's hear it.
Signal processing in this Motorola handset combined the output of the 3 microphones in intelligent ways to create directional audio beams. When I'm on this side of the handset, my voice is amplified by the beamformer. When I'm on this side of the handset, my voice is suppressed. Thank you very much.
That was nice. Let's hear it again.
Signal processing in this Motorola handset combined the output of the 3 microphones in intelligent ways to create directional audio beams. When I'm on this side of the handset, my voice is amplified by the beamformer. When I'm on this side of the handset, my voice is suppressed. Thank you very much.
Okay, that was subject mode. And that brings us to the last slide. I titled this summary. I'll just quickly go over it. We looked at the need of using multiple microphones and what one can do with them. We reviewed very quickly the differential and the delay and sum beamformers, and we noticed that the benefits of using differential arrays versus DSB. We looked at some fundamental array arithmetic, and we were able to see how combining different signals can lead to a signal of desired directivity. We saw how this is useful to define the audio attributes for enhancing the camcorder feature in the Android platform. Then we looked at the practical realization of a microphone array. We showed some examples of what the array does to an actual signal. We saw a movie, and we discussed the implementation challenges of all of this, which turn out to be more varied than someone who deals with audio would like to see. In conclusion, this was, for all of us that participated, was a really interesting project, very fruitful, very interesting, with interesting and neat problems to solve, some unexpected problems to solve. And as engineers, we all like and love that. So now is the time for questions, if there are any. If there aren't, I know everyone has turkey on their mind, so we can go on our way. So. Okay, how do we handle this? Because I don't know your names, and there was a gentleman up there who, yes.
I guess one thought that comes to mind, you talked about implementation challenges. Obviously that in itself is a pretty large challenge, but I was curious about user testing. Where does that factor in?
Right. So everything we do goes through a first rigorous sets of tests that are, some are automated, they're done by robots, that they look for stability. For example, there's someone who will shoot 1 million videos, a robot will shoot 1 million videos and will see if the camera will crash or bomb out. There is a set of people that are given this, and they are told, shoot the videos, see what we can notice completely blindly. So there is that. And then there are field trials where pre-release software is given, and the video camera is one of the things that they look at. What they look at is not so much directivity, but they look at other aspects. Would the camera sound very bad if you go in a very loud place? Would you be able to record a person that is in front of you? Things of that nature. And so that feature, I skipped some major parts out of it, but obviously the microphone array is only one part of it. There's other things. There's a dynamic gain processing, there's noise gating, there's all kinds of other things that happen that are irrespective of the array. But yeah, that amount of testing is done by people other than ourselves. Did that address the question, or? Well, oh, those kinds of things. No. Oh, right. Yeah, I understand. Well, much of the early work is done by the design team, and a lot of the kinks are worked out as soon as possible. And the final user, that happens when we are sending the devices in the lab or prior to sending the devices for lab testing, because they have to go to the carrier, and the carrier does their own sets of tests to them. But anyone else? Okay.
So when you're looking at the process in your traditional talking process, you have a very restricted bandwidth.
Right.
You know, as you talk about, a lot of your talk was, okay, we're going to move this to a home theater
Mm-hmm.
When you move that to a home theater environment, you now have a much broader playback environment, and the dimensions of the phone are now much larger than where wavelength for part of that.
Right.
What do you do in those upper frequency bands?
That's a secret, but like I said, I mentioned some possibility. There's various possibilities. What one can do is bandwidth limit the device, bandwidth limit the processing, and just get the benefit in a bandwidth of interest, or not do anything if they wanted to, and just take into account that the directivity in a room with all the reflections in these upper frequencies is what it is. And so this will not even make a lot of difference in that environment. There's various things. I think I wanted to mention that in itself becomes a challenge. Why? Because the microphone comes in from the manufacturer and they have some resonance, and that would be, let's say, 17 kilohertz or 20 kilohertz, depends, the actual piece, the actual mic. And so when that is ported, that resonance becomes lower, much lower. In the voice use case, no one cares. In this full bandwidth use case, all of a sudden, we care. And so what do? Well, we have to go and tell the manufacturer, could you please do something about it, make the resonance as high as possible? Why is always the question. Why do you want that? It's difficult. Anyone else? Yes?
I find when I'm shooting movies with my phone, I'm torn between different situations. Probably the most common is I want to narrate something, send it to somebody, and often it's quite noisy.
Right.
And I found that typically using the microphones that I might not even know where they are in the camera usually doesn't work out too well.
Right.
But what I found usually works better is to take the microphone that comes with the phone for sailor's use and close talking. That seems to work always the best.
Right.
But that's a different deal. But in your discussion, you're talking about, is there a speaker in front of the device or behind? Do you attempt to try to figure that out based on the sounds around the camera, like I'm narrating or somebody's talking, and then do any kind of...
I understand. No, in the current implementation, I had somewhere in the slides automated control of the camera. At the moment, we do not do that, but it's certainly a possibility. It's just a question of having resource to look at that, but it's certainly a possibility. I will add to that all of this was talking about menus. If you look at our current products, there's no menus. Nobody wants any menus. Nobody wants to touch the device. We should talk to it only. So,
well, sometimes by analogy with these phones that allow you to have FaceTime, you can alternate the cameras.
Sure.
I want to show you something, or to see me. Can you alternate the microphone?
Oh, certainly. Because when we do that, when that is done, when we select one camera versus another, the audio manager or the operating system underneath knows what happens with the use case. Consequently, the code will go and will say, switch the mics or reorient them or all of that. That's a control code that the integration people worry about, and they do. There's other things like shooting the video in any orientation and things of that nature. Yeah, they know the orientation of the device and so on.
And there's a last comment. Any of us that have dealt with microphones before know that wind noise is a big issue. And typically, if you're in a professional application, you can put something around the microphone, wind screen, and so forth. But on a cellular device, appendages you don't do that.
Right.
What signal processing techniques have you found to be useful for minimizing effects of wind noise?
Right. There's algorithms that do that. Motorola, for example, owns the IP on a process that takes two signals out of two mics, but that could be extended to multiple mics, and detects that wind has occurred by comparing the energy, and that's already known process. And then what it does some energy minimization in the bandwidth where the wind would occur, where it will decide between the multiple microphones in the frequency domain the signal from which bin would it be useful in this case, because the signal that has less energy is most likely the one that has no wind noise present. And that works quite well in minimizing the wind noise. But that's not the only way to be done. There's various... Selects the lesser evil, right. And given the fact that the acoustic signal is somewhat similar, coherent across multiple mics, but the wind noise is not, by that minimization, and the wind noise is quite a bit higher than the rest of it usually, that sort of minimization can work. And there's various other implementations. And like I say, that's not very cheap computationally to do, however.
Thanks.
Anyone else? Yes?
I was wondering if proximity effect ever became a noticeable factor in these type of arrays, or if the spacing was going to create proximity effect where when you're speaking very closely to a directional array, like the low frequencies would get accentuated.
Right. So in this application, we do not worry about that much, because typically you cannot speak very close to the array, because your nose will fill the entire viewfinder, right? But at the AES, the same conference that we talked about this, there was a fellow from Bell Labs, and he looked at precisely that application where they would measure and automatically detect the bass effect, and they would correct for it. So that's something that people are working on. I think there was another question somewhere. Was there anyone else? Don't want to offend anyone. Okay.
By how much the wind noise could be reduced compared to just sound reduction?
By how much? I can't really state a figure, but it'll be multiple dB. It'll be more than 6 dB. It's noticeable, put it that way. It is, right. But again, disclaimer, this is not in our implementation. It is IP that we own. Okay. But it's noticeable. I mean, it is. Was there anyone else? Yes?
For the multi-mic, when you plug the mic, you need to pair that mic.
Yeah, the microphone noise, typically we require, well, everyone wants the microphone noise to be as low as possible. In this case, when we do the differential array, because we are losing low frequency due to the differentiation, the lower the noise, the better, obviously. But we are limited by what is available on the market. So put it that way. I don't know if that addresses the question or not. Because theoretically, if there was no noise present, one can take this signal, which is high pass, which looks like a high pass filtered signal, and can equalize it all the way to DC. Practically, that cannot be done, because we will hit the noise floor and we will just increase the noise ad infinitum. It would be a very, very bad idea. So what we end up doing is a compromise where we try to get as low as we can go, closer to the full band signal, closer to the lower end. Another problem with that is that we have to worry about environmental noise, like a loud car or a bus that has subsonic frequencies. And if we were trying to expand as much of the low frequencies, we will end up with a bad effect. Simply because we'll be saturating the mic with a signal that isn't very useful. Anything else? Okay.
Thank you so much.
Thank you.
I have a certificate of appreciation for you.
Oh, thank you.
Your very
All
own
right.
AES mug.
Excellent. Thank you very much.
And the traditional photo.
All right.
Yeah? All right.
This looks like an
Backup.
iPhone. Oh, okay. Oh,
Yeah. Sorry about that.
Oh, no. I thought that Riva brought it, and I was like, what happened here?
All right. Okay.
All right.
Thanks.
Thank you very
Excellent.
much.
Thank
Thanks
you
for
so much.
inviting me. Thanks for all the good questions. Thanks for the attention. And
Excellent.
have a good holidays, everyone.
Happy Thanksgiving.